We're now going to turn our attention again to some topics related to atomicity, and this is necessary in order to finish off one piece of assignment 2B. So we're going to talk about volatile variables today, and we'll explain how volatile variables allow concurrent Java programs to use thread-safe mechanisms that enable atomic reads and writes from single variables. When a concurrent program is not written correctly, the errors tend to fall into one of three categories. Either you have atomicity problems, you have visibility problems, and/or you have ordering problems. So those are the three kinds of things that can go awry. When you use volatile, which is what's called a type qualifier, it ensures that any changes to a variable are always consistent and visible to other threads atomically. Kind of like the Star Trek transporter beam. You beam all or nothing. What happens here to ensure this is that reads and writes go directly to memory, bypassing any registers, any cache, and so on, in order to avoid so-called read-write conflicts with Java fields. Volatile reads and writes cannot be reordered. They have to go through in an atomic way. So you'll end up basically with these atomic read and write or acquire and release pairs. It's as if you have sort of like a synchronized section for data access. That's sort of the way to think about what a volatile is. It's actually a very simple concept, but one that is surprisingly subtle to use correctly in practice. If you're writing a sequential program, then volatile is simply not needed at all. Reads and writes of most Java primitives like ints, shorts, chars, and so on are already defined to be atomic. However, for certain types, in particular longs, it's not guaranteed to be atomic. So if you have a Java program where you have some thread that writes to a non-volatile field, then the next read of that field will get the value if there's only one thread. So if you only have one thread and you write, then the next time you read, you get the update. And of course, that would work perfectly fine because it could be cached, but it wouldn't matter because there's only one thread of control. So if you're reading out of the cache, you're reading out of the same cache because there's only one thread. When you use multiple step operations for things like longs and doubles, there can actually be multiple operations. So if you have modern architectures where you've got, say, 32-bit access, where the word length of bus access is 32 bits, then things that are 32 bits and smaller will work just fine atomically because you only need one read or write to read or write them. But when you start working with quantities that are larger than one word, like a long or a double, then it would require multiple operations. And then if you have multiple operations, unless you're in one thread of control, you can have things sneak in and end up with contention and read-write conflicts. So for single-threaded programs, this whole issue is really not an issue. For multi-threaded programs or concurrent programs, it can become an issue. And that's, of course, where volatile plays a role. And the reason for this is that one thread may not see the latest value of a variable that's changed by some other thread due to caching effects. So let's assume, for sake of argument, that we've got the following. We've got 3 threads running on 3 different cores, and at some given point, they've all got caches that reflect what's currently in main memory. So each core has its own cache. If thread 1 writes a value to a non-volatile field, which we denote as NV, then that will be cached locally in thread 1's cache. So you can see that the value of NV is 7 here in the cache, but it's not actually reflected in main memory, and it's also not reflected in caches that are accessed by the other threads. Therefore, when thread T2 reads the value of field NV, it can get a different result than what would be in thread 1's cache because it's reading it from main memory, but this cache has not been flushed to main memory, and that main memory value has not been flushed to the other caches. So as a result, we'll have inconsistencies. This thread would see NV having the value of 7. This thread would have NV having the value of 42. Those are obviously not the same value, so we have inconsistency, which is one of the problems with concurrent programs. And this falls under the general heading of consistency. There are inconsistent results in different caches. Not surprisingly, Volatile will solve this problem. So the Volatile keyword is designed to address the problems of concurrent access. And it's interesting because this is one of those keywords, this type qualifier, that also exists in C and C++. But interestingly enough, in C and C++, volatile has a different meaning. And so if you come from the C and C++ background, it's easy to get confused as to what its meaning is because it's not the same as in Java. What it means in Java is that a value that's written to a volatile variable will always be stored in main memory, and it'll essentially not be stored only in the cache. I mean, it could be updated in the cache, but if you write 7 to a volatile variable, a variable that's qualified with the volatile keyword, then of course it'll update the cache, but it'll also go ahead and update main memory as well. And therefore, if someone writes a volatile variable, it'll go into main memory, and then when someone reads it, it'll get the right value. So if a thread comes along and reads a volatile variable, it will not be resolved in its cache. It'll instead have to go back to main memory and pull it out of its main memory location. And again, it may cache it. That's a sort of an implementation side effect. But it will enable this thread to get the same value that was written to previously in thread T1. And the thing to remember is that volatile reads are cheap. They're very cheap. And volatile writes are cheaper than using synchronized statements. So volatile is sort of baked into the Java memory model in a more fundamental and efficient way than using synchronized statements. They're basically lightweight synchronized statements that only affect a particular field from reading and writing to it. Volatile also guarantees atomicity, even for types that are bigger than the size of the bus. So if we were on a 32-bit machine, a machine where word size is 32 bits, and we define a long, which is 64 bits in Java, guaranteed to be 64 bits, if we don't put volatile here, then we're going to potentially end up with some weird results. So let's take a look. First, let's take a look at what happens if we put volatile here. So if we put volatile here, and then we assign A to some funky value and B to 0, and we spawn a thread which is going to basically iterate effectively forever. And every time we go through this loop, we're going to set the value of foo to be A if the current loop counter is even, and B if the current loop counter is odd. So this thing just sits here and loops forever doing that. If you take a look in this other thread, it's going to go ahead and read the value of foo, and it could turn out that under some circumstances, if you read the value of foo and compared it to A, and you read the value of foo and compared it to B, if you put volatile here, you'll be fine. It'll always be either A or B. But if you don't put volatile here, if you take volatile off as a type qualifier, then it could very well be the case that the value of foo is some intermediate value that's somewhere between A and B because of the fact that that requires two operations to read and write the values. So writing the values up here and reading the values down here. So you could end up with sort of inconsistent results, which will be a problem. And there's a nice Stack Overflow article that talks in more detail about why you would want to use a volatile long, and I think this example comes from that discussion. Okay, as you might imagine from looking at this code, this is a ridiculously subtle problem. And so you have to know how to use volatile correctly to avoid these kinds of inconsistencies. And this kind of problem would only show up sort of in a blue moon, and it would only show up if you ran on certain types of hardware, like an older x86 machine that was 32 bits and so on. That would be very confusing to try to debug that code. So reads and writes are atomic for all variables that are defined using volatile, and that includes longs and doubles. So they're all used in a consistent way. If you use references, where you say such and such equal new foo f equal new foo, or foo is some class. References are always atomic. So reads and writes of references are always atomic. You don't have to mark them as volatile to get them to be atomic. Volatile also guarantees visibility. So remember we said that there were three things. There's atomicity, there's consistency, and there's three properties of visibility. Three properties of atomicity. We have consistency and visibility and ordering. So here's a case where volatile will guarantee visibility. So we're going to define a class which is going to implement runnable, and we're going to define a field here that's called is stopped, which will be set equal to false, and we're going to define it as being volatile. And basically the idea here is we have some run hook method which is going to run in a loop in a background thread, and it's going to keep looping while it hasn't been stopped. And what we want to do is if someone calls the stop me method, we want to make sure that we set this flag in such a way that it will be visible to another thread. So if thread T1 sets m is stopped to true, we want thread T2, which is running this loop, to be able to detect that m is actually stopped. And if you didn't use volatile, then you might never stop. So that's the basic problem that we're addressing here. So if you use this as volatile, then it's going to be stopped because it'll set that flag, and then that'll be propagated through the main memory so that next time this thread reads m is stopped, it'll read it from memory as opposed to reading the local cache value. Volatile also guarantees ordering. And once again, the ordering constraints will dictate when operations are seen to occur in other threads. So the write to this value must happen before the read here completes. So another way of saying this is these are atomic operations. They're all or nothing. Now, an interesting thing about volatile is it only applies to reading and writing it. It only applies to single operations that store a value or read a value from that field. It does not apply to incrementing something. So if you have a volatile integer or a volatile long or a volatile character or a volatile double or whatever you have, then incrementing or decrementing, for that matter, are not going to be guaranteed to be atomic. And here's the issue. So you can see here, if you have two threads that are trying to increment a volatile at the same time, an update can be lost. And that's because incrementing and decrementing of a primitive actually involves multiple steps. So the first thing that happens is you read the value, so that comes into your cache from memory. Then, and let's say these two threads both go ahead and read the value and they both have 0. And then one thread increments by 2, one thread increments by 1, and then they both write back at the same time. Well, there's nothing in volatile that will guarantee that all of those steps, reading, incrementing, and writing, occur atomically. Any given step occurs atomically, but all three of them together will not be guaranteed to occur atomically. So incrementing and decrementing volatile actually is not going to be atomic. Only reading and writing to it, a given value, will be atomic. And if you need atomic increments and decrements, then you want to go and use methods like get and increment, or increment and get, or get and decrement, or decrement and get, that come from the various atomic classes in the atomics package, which use those compare and swap operations that we talked about previously. So those are done in a slightly different way, and they are guaranteed to be atomic. So that's the overview of volatile variables, giving you a sense of what they are conceptually. We'll talk in a second about how they get applied and so on, and how you can use them in practice.